Hello and welcome to session number 14 of my lecture on statistical energy analysis and hybrid methods. After dealing with fluid systems, we will now talk about structure systems, which will be kept quite simple, simply due to the fact that structure systems are very complicated to simulate unless you have very simple systems. So before we start, some remarks. When we talk about structural systems, this is really a natural field about for finite element simulation or numerical simulation in general. Why is that? A simple analytical solution is not available. We have complex geometry, we have very complex connections and a huge set of materials, and this cannot be simulated by a simple analytical approach. So as you can see, just imagine this is a typical example for a fuselage section of an aircraft. Just imagine all the different colors, different property, different material, different kind of material. So I think it's quite obvious why this must be a typical application of numerical methods, where you can separate all this in small tiny elements, so-called finite elements, and then describe everything by discrete matrix. And due to the fact that we have this complicated situation in structures, we will in the following describe all our deterministic systems by discrete matrix equations. The structural and also the acoustic ones. Good. So what are the degrees of freedom? When we come to structural systems, we talk about displacements. These are the displacements, all space dimensions, but also the rotations. And forces, and logically, as we are talking about rotations, also moments. In classical finite element models, rotational components but are only considered if they are a really dedicated degree of freedom. So this is the case, for example, for plates, shells, or beams, for example. The coordinates that we are using are, as mentioned, the displacements u, v, and w. So in x, y, and z direction, the rotations around the axis in x, y, and z direction, and the according and related forces in x and y, z, and also the moments. In a common description, this is the discrete equation that we are forming. This is our stiffness matrix, dynamic stiffness matrix. Here we have all the displacements collected, including rotations, and here all the forces, or in short, and in the matrix and vector convention written like this. Again, so Q is the vector of the generalized displacement. Why generalized? Because it could be anything. It could be a mode shape, it could be displacement, but it could also be a rotation. This is why we say generalized displacement here in this context. And F, this is the generalized force, including forces and moments related to the accompanying displacement or generalized displacement. Due to the fact that the natural degree of freedom in our structural description is the displacement, we change a little bit. In acoustics, it's common to use the impedance, but here we switch from the impedance to dynamic stiffness, which is not a big thing because we have a clear relationship between the velocity and the displacement by using the j omega factor. The same, that means that for this, if we would like to convert from impedance to stiffness, we just have to use the same conversion here. Okay, so now let's come to our single example for a structural system. This is the homogeneous bending wave equation that we are applying to a plate, a rectangular plate in our case. As you can see, this is the equation for bending waves, where we have a force distribution that represents a point force in z direction somewhere at the plate. And this is the homogeneous, and this is the wave equation for the displacement in z direction. It would be homogeneous one if this would be 0. In our modal test case, we take quite practical boundary conditions, so the translations are fixed here around the edges, and there is no moment applied. So we say that they are translationally fixed and rotationally free. Sometimes this kind of boundary condition is called simply supported, which you find very often in the context of finite element analysis. So describing this in detail, we would define the following boundary conditions at the edges denoted by 0 or x or lx, whatever, to find the right coordinates where we have the edge of this plate. The solution of this equation is quite simple. Again, we have our famous mode shapes, which are sine functions here in this case. The reason is that they have to start at 0 at all the edges. And the related frequency to all those frequencies are given by this equation here. And also the related wave number is given by those equations here. Okay, good. Again, we use a combined index. So it's just a double index here. So we only have index and x and y direction because we are talking about a plate, a so-called two-dimensional system. Good. Those mode shapes can be normalized, and we do so if we just integrate over the surface of the plate. And the result of this surface is that we got the product of the length. And they are also orthogonal. So if the functions are not having the same index, it will be 0. That's the reason why we use a Kronecker symbol here. I'm not using the specified Gauss theorem. This is an outcome of just trigonometric integrals. If the sine function has the indices as used here, it will be 0. No? Good. However, using the result of this integration, we can create normalized shape functions so that we just have as a remaining Kronecker symbol that we take the square root as normalization for every mode, and the normalized modes are used by the phi symbol and not the psi symbol anymore. Okay, so how would such mode shapes look like? Here's just an example of some modes. I mean, that's obviously, this is something that you very often see in plate theory, typical vibrating shapes of a plate. So similar to our room acoustic or one-dimensional considerations, we also have to find a simplified formula for our modal density. And we use the same trick as we have used before. We take the mode count estimation by just taking the area that is required for is occupied by one mode by taking the rectangle here again. And however, due to the fact that we have dispersion, we cannot take the frequency axis anymore. We have to rely on the k on the wave number axis because they are regular. We would not have regular grid if we would use the frequency axis here. In addition, the thing is quite much easier than for rooms or other systems because we have no tangential modes. There is no static mode and there is no index 0. That's because we have not using cosine functions, we are using sine functions. So all the fancy half columns here, the corners as was used in the fluid example, they are not needed anymore. And the formula for modal density is quite simple. So we just take the quarter circle with radius pi k squared divided by 4. And we have to use the wave number rectangle, which is given by pi squared divided by the length of the plate. And then we can estimate the mode count. From this, we can calculate the modal density by using the derivative of this. And if you go to the details of all the steps, we get a quite surprising result. Due to the dispersion of the bending waves, the modal density is constant over frequency. So it's everywhere the same. However, one thing you have to keep in mind, this is only valid for the Kirchhoff approximation, which is a very simple one. It would be slightly different if we talk about more precise plate equations, but for the Kirchhoff approximation and for many thin plates, this expression is true. The modal density is constant over frequency. Okay, good. So next step is, what do we do with the modes, despite the fact that we can describe the statistics of our plate here? The next step is to use the modal response to calculate the response to specific force excitations. And again, we use a double sum, but using now the single index, running over all the mode shapes with the modal coordinates, again denoted by the prime. When we enter this into the wave equation, in homogeneous wave equation, we will get this result here. So, and to solve this, we multiply with the mode shapes m from the other side and perform a surface integration. And then we get, as a result, using the orthonormal effect and so on, we get the response for all the modal displacement coordinates from here, coming from this expressions here. We need the force, we need the modal force, and just the difference of frequency, all those things that we knew from classical modal descriptions. What is the description of this modal force? It's the surface integral of the mode shape multiplied by the force density. Why force density? Because that's the classical point force. So why do we use a force density? We need a density description to overcome the surface integration. And this is done by using the two-dimensional delta function, which creates a force density denoted by the 2 primes out of our specific force excitation here located at positions x0 and y0. That means if we enter all this into the equation and using the modal coordinates, we get as the displacement of our wave shape due to one specific force excitation at the coordinate x0 and x and y0, we get this frequency response. So we have now an equation on board where we can quite easily calculate the response to a specific force excitation located wherever you want at the plate. If you have more complex excitation, you can do the same, but then you will get a different, you get a totally different expression for the force excitation. Next step is that, as mentioned, we are very interested in the mechanical point impedance. You see where this is leading to, because we're just interested in what happens at high frequencies. We just have to calculate the impedance. So we take the force and divide it then by the velocity. Sorry for that I'm still using the impedance, not the stiffness. We come later to the stiffness. And if you do so for one specific plate, we see the typical and general effect. So this is the curve of our, this is 1, because this we just present here the frequency divided by the free field impedance. And if we do so and divide that, we see the typical effect. We have a deterministic behavior of the plate at the low frequencies. So this is our infinite impedance formula for the infinite plate. As you remember, this is completely frequency independent. And you see that the impedance goes to 0 and the real part is approaching the value of the free field plate. It is not so well approaching as the room example or other examples, and the reason for that is the constant modal density. Because as you remember, the modal density stays constant, and that means the number of modes is not getting nearer in the frequency band. That means that this overlap is not getting higher and higher, so we just have other effects here. So that means that we really are not perfectly approaching the free field point impedance, but we are approaching it. We will see later if this gets better if we do a random analysis, just doing some modifications of many plates. But again, this not so perfect approaching is an outcome of the modal density, which is always constant. Good. So far for our again proven far field approximation for high frequencies. Now we have to talk about another fact that is very important in acoustics and vibroacoustics, the principle of reciprocity. When you inspect the equations before, you can see that the force at one position and the velocity at the other position can be exchanged. So it is from the formula exactly the same principle if you are exciting here and taking the frequency response here at the plate, or you do it exactly the other way around, so that you excite here and you measure the acceleration as this part at the plate. And this is what we call the reciprocity principle. So the relationship of displacement at 2 to force at 1 is the same as the displacement at 1 related to force at 2. There's those quantities, they must be power related due to the principle of reciprocity, and that's very important. And as you know, force divided by multiplied by velocity would be the power. So, but you might say, okay, this is a displacement now or an acceleration. Why can I use this? I mean, one thing is clear: with an additional time derivative applied by this factor, we can modify this and we can always get back to a power expression. And just the factor here does not make this value here untrue. In addition, so what is the consequence? The consequence is that the reciprocity is also valid for displacement acceleration. However, on top of that, it's a global principle. And it's also valid for coupled vibroacoustic subsystems. And just have a look at this example here. It could also be the same, and this is very often used in experimental techniques. If you have one experiment would be to excite, for instance, here the front axle by a force and measure the pressure, would give the same result as if you would apply a volume strength here in the car and measure the velocity at the axle. So, for instance, if you would just interested in one response here and you would like to measure all the different responses, it's much easier to just take one volume source and measure all the acceleration here instead of applying forces everywhere on the different axles. In formulas, it would look like this. So the measured velocity at position 2 related to the excitation at Q is exactly the same result that you would get if you would apply a force at position 2 and measure the pressure at position 1. One thing that people very often confuses, must not be mixed up with the fact that the wave field or the shape is the same. That's obvious. I mean, if I excite here, we'll have a completely different wave form here at the plate as you would have when you would excite here. It's just a statement about the different responses here. It has nothing to do with the shape of the total response shape of our plate or the pressure field here in the car. Okay, let's come to the conclusions. So we have, and for all of them, for all structure and fluid systems, we have derived statistical criteria as modes, mode count, and a very important modal density for academic systems, and also important for academic systems. A tube, a rectangular room, or a rectangular plate. We will apply those systems to Monte Carlo simulations to investigate the statistical methods in more detail. The power input is similar to free field sources for high frequencies. So under consideration of a near field boundary, that means if we have a large system and put let's say a loudspeaker at the wall, or if we use a force on a plate, for high frequencies, the radiation of the power and the introduction of power is the same as if it would be an infinite plate. So the power introduction to an infinite plate high frequency is similar to the power introduction into an infinite plate. And this is the main assumption used in SEA for later connecting subsystems, because this is always done in high frequencies, and you will learn later what are the conditions that are required that this assumption is correct. And last but not least, realistic and industrial examples require numerical methods. Definitely for deterministic, but, and please keep this in mind, also for random subsystems. One argument against SEA very often is you have no simple description of a very complicated part of a car or whatever of a fuselage. Yes, that's true. But there are other methods to get the random description also out of a numerical description. Good. So that's it from my side for for structural systems. The next session will be talk about a very, very important thing. We will look into the statistics and the physics and especially this and also the stochastics between two positions in diffuse wave fields, and we will do this for all available or all important dimensions. So 1, 2, and 3-dimensional systems, and this is a real major step into the first description of a full SEA subsystem. Have fun. I hope you enjoyed this lecture and see you later for session number 15.